Hi everyone. Today we are going to study a type of graph that is very important both in theoretical computer science and in many applications. I'm talking about trees, and we are going also in a future lecture to study what we call tree traversals, which are ways of working with the trees, visiting every node in the tree, and doing some operations with the data that we have in the tree. Okay, and you will see that this is very important in many situations. Okay, so you may remember that we have already talked about trees. For instance, we have talked about derivation trees when we're studying formal grammars and the problem of ambiguity and how to capture the structure of a given sentence in a grammar. Okay, so we defined a special kind of tree that was related to the way in which we derive the sentence in the grammar. Okay, but today we are going to formally define what we understand in graph theory by a tree, and to study some of its properties and to see that it is a kind of structure that you are going to be using in many different courses and in many different problems. Okay, so mathematically, is a tree is an undirected graph, a graph in which the edges have no direction, that is connected and has no cycles. Okay, and here be careful, because when I'm talking about cycles, I'm referring always to simple cycles. So for brevity, I'm not writing all the time that a cycle is simple, but in the context of trees, cycles are to be thought as simple. Why do I say this? Because of course, whenever I have at least one edge, let's say that I have one edge between 1 and 2, I always have cycles that are not simple. For instance, I can go from 1 to 2 and then go back to 1. So this is of course a cycle. It's a path that starts and ends in the same node, in node 1. But it's not simple, because this edge here and this edge here are the same edge. Okay, so when we talk about trees, we talk about cycles that are simple, because in any other situation, if I have an edge, I always have a cycle. And if I want to impose that there are no cycles, uh, if I don't think about simple cycles, then any graph that has at least one edge would have a cycle, and that is a not very useful notion. Okay, because if I don't have any edge, then I cannot do represent any useful situation. Okay, so in the context of trees, when I talk about cycles, I talk always about simple cycles, cycles that do not use the same edges more than once. Okay, so once that we know about this important distinction, we can define a tree as a connected graph which is undirected and has no cycles. Okay, so let me remind you that when we have, for instance, tree for a derivation, for instance, imagine that I have something like this. Okay, this is a derivation of a word in this grammar. Okay, this is indeed a tree, because this graph is not directed, it is connected, and there are no cycles, there are no simple paths that start and end in the same vertex. If I go, for instance, from S to A, then I cannot go back with a different edge, okay? And if I go from this S to lambda or from B to S, I cannot go back to B because there is no other um, edge that allows me to go back, okay? I should use the same edge, and remember that we are talking about uh, cycles that are simple, that do not repeat any edge, okay? So this definition of tree includes the kind of trees that we already know about, okay? Um, this is a definition that encompasses the kind of structure that we already know about, okay? And here in the figure, you can see an example, a more complicated example of a tree, okay? So this is a graph that is obviously connected, and you can see that there are no cycles, okay? So this is a tree in the sense that we have just defined. We can also talk about forests. Forests are, as you can imagine, sets of trees, okay? So for instance, here I have a graph which is not connected, but since it has no cycles, each connected component is a tree. So here I have a connected component, another connected component, and a third connected component. And each of these connected components is a tree, okay? So the set of all these connected components, the whole graph, is what we call a forest. So a forest is a graph that has no cycles, okay? Because then each connected component is a tree. So this simple definition is all that we need in order to work with this structure. A tree is just a connected graph without cycles. And why are these trees important? Well, they are important because they appear in many different situations, okay? These are a special type of graphs, and graphs, you know, that appear in many different situations, but trees are also very common in many applications, okay? So for instance, uh, we already know, I have just mentioned that we have already studied an application of trees in the study of formal languages by means of what we call derivation trees. We already know about them. We will study in a future lecture a way of evaluating arithmetical expressions by means of trees, okay? So this will be also important in connection with the study of syntax analysis and of formal languages and how to evaluate the semantic properties of languages, because they allow us to evaluate values of expressions written, for instance, in a programming language. Okay, so these are examples that are important to us in this course because they are related to things that we have already studied. But you will find trees also in future years, in future courses. For instance, when you study data structures, and you will study a lot of different search trees. Search trees are data structures that allow us to make uh, search tasks fast. Okay, so we have a lot of information and we want to search for a certain piece of data, and if we have this data in a search tree, then we can quickly recover the information that we are looking for. Okay, and you will study balance trees and B trees and different kinds of trees that you will implement, and you will see the different properties and when it is better to use one kind of tree or another kind of tree for search tasks. Also, of course, you know about trees. Uh, when you talk about the file systems of operating systems. And when you study operating systems in a future course, you will study trees, because the file systems with the root folder or directory of a hard drive, and then all the different folders in the hard drive is also a tree, okay? And it's a structure that you need in order to um, make a file system in a hard drive, okay? Also, it's the notion of tree is something that you use in artificial intelligence. For instance, related to decision trees, which are a way of constructing machine learning models that allow us to take decisions to classify objects according to some rules. Okay, so you will study this in intelligent systems, I guess, in your fourth year, and you will study different types of decision trees, like for instance, the famous C4-5 or IB3, and you will see that your model will be written as a tree, okay? And also, among many other different applications, you have game trees in artificial intelligence. So game trees are ways of representing the different situations in a game. Okay, so let me give you an example with a very simple game, the game of tic-tac-toe or three in a row. Okay, where you have to write different elements, crosses and circles, and try to get three elements in a row. Okay, I think you all of you know about this game. So we can represent the different situations in the game in a tree, because we start with the initial position, and then we can have uh, different situations. For instance, if the first player chooses this square, this cell, or if the first player chooses this other cell, or if the um, first player chooses, I don't know, this cell, and so on, up to the 9 different possibilities that the first player has. And then from each of these, we have the different possibilities for the second player. So the second player may choose this situation, this position for his circle, or I don't know, this one, and so on. And from here, the second player can play their circle here, or in this in this other position. Okay, so from each possible position, we have then several different replies by the other player, and we can have this tree. And searching for a way of playing the game, a strategy to win the game, has to do with finding some interesting position in this tree. And there are different ways of evaluating the positions in the tree, and of finding an interesting way of winning the game in this tree. Okay, and this is a very important topic in artificial intelligence and in computer games. And there are different ways of trying to simplify the number of positions that one has to evaluate, because as you can see here, the number of positions, I have not written all the positions here by any means, and the number of positions grows very rapidly. And in games like chess or Go, where there are many more options than in this three in a row game, you have a lot of positions in the tree. Okay, so you need to find a way reducing the complexity of the tree, okay, and that is very important. How to evaluate the positions, how to traverse the tree, or find for some positions in the tree in order to have a good way of playing the game. Okay, so as you can see, trees are very important in many different situations. Okay, and we will study here just a few of the properties of trees, and you will further study this data structure in future years, in future courses. And today we are going to give some important properties of trees, and we are also going to give some notions related to trees and to what we call rooted trees, trees in which we have a special element, a root. Okay, so in this slide and the next, I'm going to prove some properties about the number of edges and the number of elements, the number of vertices in a tree. What is the relationship between the different elements in a tree, the edges, the vertices, and so on. Okay, so I'm going to mathematically prove some theorems, some results. You don't need to learn these proofs. You don't even need to understand every little detail of the proofs, but I want to give you at least the flavor of the kind of theory that we have behind trees, and what are the mathematical ways of dealing with these objects. Okay, remember that this course has a deep mathematical uh, theory behind, although we do not study all the proofs and all the notions. Okay, but I want you at least uh, to have an idea of how to prove this kind of thing. Okay, so the first thing that we are going to do is to show that we have a relationship between the number of edges, which we are going to call E, and the number of vertices whenever we have graphs that are either connected or don't have cycles. Okay, so in both cases we talk about the number of vertices, which is n, the number of edges, which is e, and we are going to prove a relationship between them when the graph is connected or the graph does not have a cycle. Okay, so the first thing that I'm going to prove is that if the graph does not have a cycle, we are always talking about not directed graphs. If the graph does not have a cycle, does not have a simple cycle, remember, um, we have this relationship between the number of edges and the number of vertices. The number of edges is at most the number of vertices minus 1. Okay, so it means that if we have more than n minus 1 edges, then we at least have a cycle. Okay, so any graph that has no cycles has at most n minus 1 edges. Okay, and let me give you an example and then a clarification, a warning about how not to interpret this result. Okay, so first of all, if we have a graph that has no cycles, it can be something like this, for instance. Okay, and it doesn't have to be connected, so I can have something like this over here. Okay, so in this case, let me give numbers to the vertices: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and 14. So n is equal to 14. Okay, and the number of edges: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And in this case, the number of edges, E, is equal to 12. So in this case, clearly 12, which is E, is less than n minus 1, which is 13. Okay, so as the theorem or the lemma stated, the number of edges is at most the number of vertices minus 1. Okay, and this happens with any graph that does not have any cycle. But be careful, because we can have a situation in which the number of edges is less than the number of vertices minus 1, and even in that situation, the number of the graph does have a cycle. Okay, so this goes in this direction. If there are no cycles, then the number of edges is at most n minus 1. But there is no implication in this direction. Okay, so I can have a graph in which the number of edges is less than the number of vertices minus 1, and it has cycles. For instance, consider this situation. I have this situation in which I have 1, 2, 3, 9 vertices in total, and I have 6 edges. Okay, I have 6 edges, and clearly E is less than n minus 1. Okay, but we have a cycle here. Okay, so the result goes in this direction, not in this direction. Okay, what we can say is that if E is greater than n minus 1, then we have cycles, at least one cycle. Okay, but not that if E is less than n minus 1, then we do not have cycles. Okay, because in fact this is exactly the same, is logically equivalent to saying that if we do not have cycles, then E is less than n minus 1. Okay, so be careful with this distinction. Okay, and now with this remark in place, let me prove that if the number of edges is less or equal than n minus 1, then if we do not have cycles, then the number of edges is at most n minus 1. That is what we want to prove. Okay, so we are going to do this by induction in the number of vertices of the tree. We are going to start with the simplest case. We are going to suppose that the theorem is true for graphs with up to n minus 1 vertices, and then we are going to prove it for n vertices. Okay, so the first case is when we have just one vertex. Okay, and in that case, the only graph that we can have, since this is an node-directed graph, and then we do not have loops, is just a single vertex. And in this case, E is 0 and n is 1, and of course we do not have cycles, and E is exactly equal to n minus 1. So in the simplest case, in the base case, the result is true. So now suppose that n is greater than 1, and the result is true for graphs with less than n vertices. Okay, this is the typical proof by induction. Okay, so in this case we do know that the graph does not have cycles, so it will have some vertices here, here, maybe another one here. It does not have to be connected, so we can have something like this here. Okay, so what we are going to do is to consider what happens if I remove one of the edges. I take this edge, for instance, okay, and I remove that edge, and then I consider the graph of all the vertices that are connected to one of the extremes of the edge that I have removed. Okay, so here I'm going to have n1. This is what I'm going to call g1. So in g1 we have n1 vertices and e1 edges. Okay, and then I'm going to consider g2, which is the rest of the vertices with all their edges. Okay, so in g2 we are going to have n2 and e2, n2 vertices, e2 edges. Okay, so we know that, of course, n1 is less than n, n2 is less than n. And we also know that there are no cycles in G2, there are no cycles in G1. Because if there were cycles in any of those parts, then in the whole graph there will be cycles, and we are considering, we are supposing that the whole graph does not have cycles. And then, since n1 is less than n and n2 is less than n, we can apply the result for G1 and G2, because by induction we are supposing that the result is true when we have graphs which have less than n vertices. So what we know is that n1 is less than or equal to n1 minus 1, and e2 is less than or equal to n2 minus 1. This is because we are supposing by induction that the result holds for graphs which have less than n vertices. Okay, so let me write this here. It will be better. We know this, and we also know that n1 plus n2 is equal to n, because we have not removed any vertex. Okay, so all the vertices are in either G1 or in G2. And we also know that E1 plus E2 is equal to E minus 1, because I have removed exactly one edge. Okay, so now if I sum up these two inequalities, I have that E1 plus E2 is less than or equal to N1 plus N2 minus 2. But N1 plus N2 is N, so this is N minus 2. And E1 plus E2 is E minus 1, so this is E minus 1. So I get E minus 1 less than or equal to n minus 2. And if I add 1 to both sides of the inequality, I get exactly n E less than or equal to n minus 1, which is what I wanted to prove. Okay? So this is the way in which we can prove this result. Okay, so let's go back to the slide and see what the other result says. The other result says that if the graph is connected, then we have at least n minus 1 edges. Okay, so again, a remark is in order. Notice that we can have a graph in which, well, first let me give an example, and then we say about the remark. So, for instance, imagine that we have a connected graph like this. I don't know, something like that, and this connected to that, and this connected to that. Okay, so now we have 1, 2, 3, 4, 5 vertices, and then 1, 2, 3, oops, 3, 4, 5, 6, 7, 8, 9 edges, and of course E is greater than n minus 1 in this case. Okay, so for a connected graph, the result holds as we expected, but the warning is that you can have a graph, like for instance, this one here. Let me add some more vertices here, which has n equal to 7, and then E is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, and E is greater than n minus 1, but the graph is not connected. Okay, so again, remember that what we have is that if the graph is connected, then E is greater than or equal to n minus 1, but not the other way around. It doesn't imply, if we have many edges, it doesn't imply that the graph is connected. Okay, what we do have is that if E is less than n minus 1, then the graph is not connected. We do not have enough edges for the graph to be connected, because the minimum number of edges for the graph to be connected is n minus 1. Okay, so with this warning in place, let me show you how to prove the result. So what we want is that if the graph is connected, then, oh sorry, the number of edges is at least n minus 1. Okay, and we are going to prove this again by induction. So the case, the base case, n equal to 1 is again trivial. It's the graph with just one node, and in this case E is 0, n is 1, and then E is exactly equal to n minus 1. Okay, so this case is trivial. So again, we suppose that the result is true for graphs with at most n vertices, and we want to prove it for n, where n now is greater than 1. Okay, so now we have a connected graph, so we could have something like this, I don't know, something like this for here, more vertices around here, this is connected to that one, I don't know, many different edges, and the graph is connected. Okay, and now I'm going to focus on one of the edges, this one of the vertices, this vertex here. Okay, and this vertex here, let's say that it has degree, which is equal to a number k. Okay, k must be at least 1, okay, because the graph is connected, so this edge has to, this vertex has to have at least one edge for it to be connected with the rest. Okay, and then I'm going to remove this vertex. Okay, and what is going to happen? What is going to happen is that now when I remove this vertex, I don't know if the graph is connected anymore. It may be not connected, okay? For instance, in this case, this edge here, this vertex here would be isolated, okay? So when I remove this vertex with degree k, I'm going to have at most I'm going to have G connected components and G or J, sorry, J connected components, and J is at most K, the number of edges that I have removed. Because when I remove an edge, at most I create a new connected component. Okay, so maybe I remove this edge here and then I create a connected component. But if I remove this edge here and this edge here, this vertex is connected to this one, so they remain in the same connected component. But when I remove an edge, at most I create a new connected component. Okay, so I'm going to have J different graphs which are connected, and each of them has n sub I vertices and e sub I edges. Okay, and we know, let me do it in another whiteboard. We know that we have e sub I, and I, we have I that goes from 1 to j, which is the total number of connected components. And we know that each of the number of vertices is strictly less than n, because we have removed one vertex. So no graph, no connected component of the graph now can has n vertices, because we have removed one. Okay, so by induction, we know that the connected components, each of these graphs is a connected component. In the connected components, this relationship holds, because by induction we are supposing that the result is true for graphs with less than n vertices. Okay, and now we also know that n1 plus n2 plus nj is equal to n minus 1, because we have removed exactly one vertex. And we also know that e1 plus ej is equal to e minus k, because we have removed k edges, the k edges that were connected to the vertex that I have removed. Okay, so if we sum up all these inequalities, we have this inequality for 1, for 2, and for j. If we sum up everything, then here we have the sum of the e's up to j, which is greater than the sum of the n's up to j minus j, right? Because these ones are also summed up, and we have j of them. Okay, but we know that this part here, let me carry this formula to the next whiteboard. So we have here this sum, which is greater than this other sum. Okay, and we knew that this sum is exactly e minus k. And we also knew that this other sum is n minus 1. So this is n minus 1 minus j. Okay, and we also know that j is at most k. The number of connected components is at most the number of edges that I have removed. Okay, but then minus j is at least minus k, and then if I add here e, I have that e minus j is greater than e minus k, and this we know that is greater than or equal to n minus y minus j. So if I add j in both parts here, I obtain e that is greater than or equal to n minus 1 as we wanted to prove. Okay, and this concludes the proof of this lemma. Okay, as I've told you, it's not important if you understand all the details. I just wanted to show you how to prove this kind of result with a proof by induction. Okay, go back to the slides, and then notice that as a corollary of these two results, we have that, let me write it here, in a tree, we always have that e is exactly n minus 1. Okay, it's exactly n minus 1 because a tree is connected and does not have a cycle. So we have both results. E must be at least n minus 1 and e must be at most n minus 1, so it has to be exactly n minus 1. So if we go back to the whiteboard and we draw a tree, for instance, something like this, okay, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and we should have exactly 10 edges. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Okay, exactly as the results expected us to find. Okay, so this is something that we know about trees, that they have exactly n minus 1 edges. We can prove a stronger property about trees. My idea was to prove this result in detail, but since I have already proved these two lemmas with a lot of detail, I'm just going to tell you the main ideas of this proof. I don't want to bore you anymore with this kind of proof. If anybody's interested, I can do a different video. Just tell me and I upload a video with the proof of this theorem. Okay, but what is important about this theorem is that it tells us several important ways of recognizing a tree. If we have a graph that with any of the properties in this list, then we know that it is a tree. Okay, and the idea is to use the previous lemmas and the definition of tree as a graph which has no cycles and but it's connected. Okay, so of course then in a tree any two vertices can be connected, of course, because the graph is connected, and they can be connected by a unique path, by a unique simple path. Okay, because if there were two different paths, two different simple paths, then we could form a cycle. Okay, we could go with one of the paths and come back with the other path, and that would form a cycle. Okay, So that is not possible. We must have a path because the graph is connected, but just one path. We cannot have more than one path. Also, the graph is connected, but if we remove an edge, then the graph is not connected anymore. That is exactly because the edge that connects two vertices is the unique simple path that connects those two vertices. If I remove it, then those vertices are not connected anymore, because if they were connected with another uh, uh, path, then we would have different paths, and the graph would be not it would have cycles. Okay. Also, we know about these properties here. The number of um, edges is equal to the number of vertices minus 1. And we also have this property that the graph has no cycles, but if we add an edge, then we form a cycle. This is because if we have add an edge between two vertices in the graph, those vertices in the tree were already connected. And if we add another edge, then we are forming a cycle. Okay, so these are the basic ideas in the proof. If you want me to prove it in detail, please tell me, send me an email, or leave a comment in the discussion forum, and I will very happily oblige and upload a video with the proof. But well, we are already we have already spent a lot of time in this lecture, and I don't want to bore you with details that are not going to be in the exam. Okay? So what's important about this result, and this is something that I do want you to know, is that with these definitions, or with these equivalent ways of defining or finding out that the graph is a tree, we can also study and define methods that are important for different situations. There is, for instance, a problem that is very important, very interesting, which is the problem of finding what we call spanning trees, which are um, trees which are part of a graph. We are given a graph and we want to find a tree in that graph. For instance, this is important if we have a computer network and we have to remove connections. We want to remove cables without disconnecting the graph. Okay, so we start removing edges until we find a tree. Okay, so this is what we call a spanning tree. Or we have a disconnected set of computers and we want to add connections until we find um, something that is connected. Okay, so this is important in several different situations, and it's also important to find the tree which has less cost. For instance, that has less length of the cables or something like that. Okay, or less distance between different nodes or something like that. Okay, so these are what we call the minimum spanning trees. And based on these on these properties of the trees being connected, but if we remove an edge, then they are no longer connected, or the trees being without cycles, but if we add an edge, then we form cycles. We can define, based on these properties, two different important um, uh, algorithms that we call the Prim and Kruskal algorithms. Okay, and they are based, one of them into adding new edges until we find something that is that has cycles, and before that, exactly before that, we know that we have a tree. And we also have the other algorithm in which we start with the whole graph and then we remove edges until we have something that it's connected. But if we remove an edge, it's not connected anymore. Okay, so in that case, we know that we have a tree because of these properties. And you will study these algorithms in future courses. Okay, but I want you to know that the correction of those algorithms, the soundness of those algorithms comes from this characterization of trees. And to end up this lesson, let me give you a quick introduction, it will be just a few minutes, to what we call rooted or oriented trees. Okay, so in general, a tree is a graph which is connected and has no cycles. But in some situations, we want to study trees which have a special element. In a normal tree, all the elements are the same. But in some trees, there are elements which are important for some reasons. For instance, if we have the tree of a file system, then we have the root folder, and that is a different folder. That folder is different from the others. It's important. If we have a game tree, for instance, the initial position is important, is different from the other positions because that's where we start. Okay? In that case, when we have a tree with an element which is relevant or important for some reason, we call that tree the root node, that element the root node. Okay, so it's the root folder or the root position or the root element of the tree. Okay, and in rooted trees, instead of vertices or elements, we sometimes or most times call the vertices in the tree nodes. Okay, so that's why we call this element the root node. Okay, so for instance here in this tree, the root would be 7. It's a bit paradoxical that we usually represent trees with the root at the top. Okay, so the tree is somehow upside down because the root is not at the bottom but at the top. But this is the usual convention. Okay, and then if we have a root, then we have a kind of direction in the tree. We can go from the top to the bottom, from the root to the other elements. Okay, and then we have a series of names for the different elements and the different parts of the rooted tree that come both from botany and from genealogy. Okay, because you know that we can have a genealogical tree with the different members of a family and who is the father of whom or the mother of whom, and these names are adopted in the theory of rooted trees. So we say that an element is the ancestor of another element in a rooted tree if it when we go from the element to the root, we find that other element, that ancestor. Okay, and we also say in the other direction that then the element that is lower in the tree is the descendant of the other element. Okay, and the proper ancestor is an ancestor which is different from the node itself. Okay, because all the nodes are ancestors and descendants of themselves. Okay, these are very easy to understand definitions because, as I've told you, they come from names of situations that you all know. Okay. We also say that a tree, a part of a tree is a subtree if we take an element, which is now the root of that subtree, and all the descendants of that element. Okay, so that is a subtree, an element with all the elements that are hanging from it. Okay, and of course we have ancestors, we have descendants, so we can talk about parents. Parents are the ascendants that are exactly connected with an edge to the element. So they are the closest proper ascendants. And the child or the children are uh, uh, the elements that have the other vertex as a parent. Okay, a sibling, then a brother or sister, is a node that share a parent with another node. And here is where we change now again to botany. A leaf is a vertex that has no children. Okay, and in other case we say that the node, the element, is an inner node. Okay, so let me first give an example in this graph of all these concepts, and then we talk about height and depth and degree and all that, and we finish for today. So here, for instance, of course, we have that 7 is the root, okay? And for instance, 9, 10, 11, 12 are of course all descendants of 7. Well, all the elements in that tree are descendants of 7. So the descendants of 3 are 3 itself and 1 and 2. 1 and 2 are siblings, 3 is the parent of 1 and 2, 1 and 2 are children of 3, okay? 3 is sibling with 4 and 5. For instance, we have a subtree with root 6, which is 6 and all its descendants. Okay, and I think that's all the kind of definitions that we have studied today. Okay, so I think it's very easy. I have said this a bit quickly. If you don't understand, please send me an email. But I think that the idea is clear. Okay, for instance, 8 is a leaf because it has no children. 7 is the parent of 8. 6 is the parent of 5. 5 is another leaf. 3 is an inner node because it has children, and so on. Okay. So finally, let's study what we call the degree of the elements in a rooted tree, and what we call the depth and the height of the tree. So you may think, well, we already know what's the degree of a node in a graph. Yes, we do, but in trees, in rooted trees, we have a slightly different definition. Okay, because all the nodes in the tree, with the exception of the root, have a parent. Okay, so we all know that all the elements will have at least one edge. Okay, and then that edge is not important anymore. The edge that connects the element, the node, to its parent, it's not important anymore. So when we talk about degree in a graph, in a tree, in a rooted tree, we are talking about the number of children. Okay, the proper degree, the degree as we have defined the degree up to this point, would be the number of children plus the parent if the node is not the root. Okay, so be careful because here the degree is 1 unit less. So for instance here 7 has degree 3, which is exactly the same as in the general theory of graphs, because 7 is the root and has no parent. But for 3, for node 3 here, the degree is 2. It's the number of children. It's not 3. We do not count the edge that goes back to 6. We only count the edges that go down. Okay? Then we say that a tree is M-ary, for instance, unary, binary, ternary, and so on, quaternary, and so on, if the maximum degree of the nodes in the tree is at most m. Okay, so this is a bound, an upper bound on the degree of the nodes. Okay, so for instance, in this example here, the maximum degree is 3, because there are some vertices, some nodes that have 3 children, so this would be a ternary tree. Okay, and then the depth of a node is the length of the path that connects that node to the root. We know that that path is unique. Okay, so we count the number of edges and we have the depth, and this is very easy because of course the root is at depth 0, and then all the children of the root have depth 1. The children of those children, which are the grandchildren of the root, are at depth 2, and the children of those children at depth 3, and so on. Okay, so this is very easy. The depth is kind of the level in which we find the node. Okay, if we start with the root, then the children of the root, the grandchildren of the root, and so on. And the height of a tree is the greatest depth. Okay, so we count the depth of each of the nodes, and the maximum of those depths is the height of the tree. So in this case, of course, the height of this tree is 3, because that is the maximum depth of the nodes in the tree. And this is important because when you study search trees in courses in data structures and algorithmics, you will study relationships between the height of the tree, the degree of the nodes, the number of elements that you can store in the tree, the time that it takes to find an element, and so on. Okay, so you need to know these properties of the tree in order to determine what are the storage capabilities of the tree, and what is the complexity of searching elements in that tree. Okay, so this is all for today. If you have any question, please email me or leave a comment in the discussion forum. If you want me to upload a video with the proof of the main theorem, with a detailed proof, just send me an email and I will happily do so. Okay, so thank you for your attention and goodbye.